Hi students, how are you all? Welcome to PW English. This is MV Physics. Today we are going to discuss about electrostatic potential and capacitors complete summary beta. Okay, right. As everyone know that this chapter is very important chapter. Yes. So from this chapter you will be getting one question in NEET exam and you will be getting one question in JW also. Okay, right beta. So in this class I am going to cover all the key points present in each and every topic, okay, as well as I have collected the shortcut tricks for you beta. Okay, so if you remember that shortcut tricks, it is sufficient to solve the numericals. Okay, right. So after watching the video, definitely your confidence level will be reaching to the peak stage beta. Okay, right. So without wasting any time, let us start the class. Before starting the class, all of you open your book and pen. Just note down each and every point beta. Okay, it will be helpful for you while doing the revision. In revision, you have to learn these points only. It is sufficient. Is it clear? Chalo. So let us start then. So today we are going to cover this all topics beta. Okay, what is electric potential? Okay, electric potential due to charge ring. Next, equipotential surface, relationship between electric field intensity and electric potential. Next, electric potential due to dipole, potential energy due to system of charges. Next, dielectric, and next one is a polarization. Okay, right. Electric susceptibility, capacitors. So these are the very important. Pakka from this chapter you will be getting in JW as well as in NEET exam. So series capacitor connected in series and parallel, based on the topic you will be getting the question, right? So energy stored in capacitor, you have parallel plate capacitors you have. Okay, next, force between two parallel plate capacitors, series and parallel connection of capacitor. This is a very important for you, right? Distribution of charge on plates, potential. What is potential method? Okay, and next, Wheatstone bridge. Next, mirror symmetricity. Next, folding symmetricity. Okay, effect of dielectric in capacitors. So these all are the topics we are going to cover beta. Okay, next, circuit with capacitor and resistance. So how to solve that one, I will be telling the tricks also. Okay, charging the capacitor and discharging the capacitor. Okay, right beta. So let us start the first topic, that is a electric potential. So generally the electric potential is denoted by symbol V. Actually we have change in potential beta. Okay, actually we have a formula for change in potential. Remember this one. Okay, the change in electric potential formula is work done for bringing a charge from infinite at a point in the field is called as electric potential. Okay, so just remember the formula. I will be telling you what exactly this one. Okay, based on this formula you have so many numericals, you have to solve that one. Okay, see here, this is a very important formula. See here what exactly this one is, I will be explaining you now. So this is a infinite. Okay, so here is a charge I have taken. This is a very big charge, let us consider. Okay, so point charge also you can consider. This is a point charge. Is it clear? Next, at infinite I am taking a small charge q. Okay, what I am doing is I am taking this charge. Okay, I am doing some work because I am bringing this charge from infinite at this point. Okay, I am bringing this charge from infinite to at this point. Sir, why you are bringing this charge from infinite to this point? To calculate the potential of this charge at this point. Okay, why I am doing the work to bring this charge from here to here, to calculate the potential of this charge. Sir, 100% you have to do the work. Sir, why you are keeping this charge at infinite? Why you are not keeping somewhere here and here? Okay, so actually that is a very lengthy process. So to explain this one, it takes nearly about 45 minutes. Okay, but I have to finish this one in a few minutes only because this is a summary series beta. So only just remember the key points, it is sufficient, okay? Because this is not the regular class, na? If it is a regular class, of course, I have to explain each and every point detailedly for you. Is it clear? Right, beta? Now see here, so we have to bring this charge from here to here. Sir, if you bring a charge from here to here, what happens? Why you are bringing from infinite? Okay, so only one point I will be telling you here. Okay, see here, if you keep this charge here, first of all tell me, this is a positive charge, this is a positive charge, right? Positive, positive, what happens? Get ripples, right? If you keep a charge here, automatically it will be going to the infinite. Okay, automatically it will be going to the infinite, beta. Okay, if you keep a charge at infinite, then there is no force between this charge and this charge. There is no force now. Okay, so now from here I am bringing the charge and keeping it here. Okay, so actually, so this charge has a this is a positive charge and this is a positive charge now. Plus plus get ripples now. Yes, so actually it is moving in a backward direction. Okay, so what I am doing? So firstly I am applying some external force and I am bringing the charge and I am keeping finally here, beta. Okay, so I am doing the work against electric field. Okay, I am doing the work against the electric field. Is it clear, beta? So detailedly I can't explain you. So this point is sufficient for you now. Okay, so I am doing a work for bringing a charge from infinite and keeping here. Why? To calculate the potential of this one. Okay, so how we have to bring this one? Okay, we have to bring the charge Q very slowly in such a way that we have to keep that one its speed as a constant. Okay, now let us assume that at this point this charge is pushing in this direction. Let us assume that, okay, the static forces are 20 newtons. Okay, so how much force you have to apply in this direction? How much forces you have to apply? External force. Okay, 20 newtons only you have to apply. 20 minus 20 get cancelled, so its speed remains constant, beta. Okay, is it clear? So actually you have learned this all the things in your colleges, in academies, institutions, right? Somewhere else you have learned. Okay, so there you have learned detailedly, but here just remember the key point. That's it. Okay, main point is what? This formula you have to remember. Based on this formula you will be getting the numericals. Okay, chalo. So this one is clear, na? Potential at infinite, always remember it is 0. What is the potential at infinite? It is 0. Clear? Right, beta? Now electric potential versus smaller graph. See here, beta, the potential at points P. See here, we have two formulas. Delta V is equal to work done by external for bringing a charge small q from infinite to at a point in the field, right? So this is a one formula. This is a potential in terms of work. Okay, this is a potential in terms of work, external work. Okay, so this is a potential due to the point charge. This formula is, this is also potential, this is also potential. Both are potentials only. Okay, this is in terms of external work done, this is in terms of point charge, this is in terms of point charge. Is it clear, beta? Right. So what is here K value? 1 by 4 pi epsilon naught. K value is what? 1 by 4 pi, it is epsilon naught. Clear? Is it clear, beta? Sure. So this one is clear for you all. Okay, see here, there is only one charge. Okay, there is a charge here, so you have to calculate the potential at this point, which is at a distance of small r. Okay, so remember this one, very important point, beta. Okay, if there are two charges, 100% there is a force. If there are two charges, 100% there is a force and potential energy will be present. Okay, if there are two charges, okay, there will be one force and potential energy you will be getting. This topic later. Okay, force and potential energy will be present. If there is only one charge, you will be getting the electric field intensity and the electric potential beta. Okay, so the electric field intensity is what? KQ by R square, which we have learned this one in the last class, right? Next, what is electric potential due to this charge? It is a KQ by R. It is what? KQ by R. Is it clear, beta? Is it clear? See here, this is what? Vector quantity. Already I taught you how to solve the vector quantity numericals in the last class, right? So I have taken the forces F1 and F2. Okay, so if the angle between the F1 and F2 is theta, the net force I have said you in the last class now. Yes, if the forces are same, okay, if the angle between them is 0 degree, 30 degree, 60 degree, 90 degree, 120 degree, 180 degree, in each and every cases I have given you the formulas, right? I said you that they are the very important to solve the numericals, correct? Yes, beta. So see here, that trick will be applicable for from kg to PhD, beta. Okay, if it is a vector quantity numericals always will be, all numericals will be done in the same manner. Okay. Yes, beta. Chalo. So scalar quantity numericals, as everyone know that directly addition we have to do now. Yes. So I think you have solved this all the numericals in your classes, right? Let it be. So see here, if there are two charges, 100% he will ask you the force, or else he will ask you the potential energy. Okay. For potential energy, you require the two charges, and for the force also, you require the two charges. For electric field intensity, you required only one charge. Okay, you required only one charge. And for the electric potential also, you required only one charge. It is sufficient. Is it clear, beta? See here. Here, force. For force, you required the two charges, K, Q1, Q2 by R square. For electric field intensity, you required only one charge. Correct? Both are what? Vector quantities. Okay. Now see here. Electric potential in terms of dielectric. Okay. Relative permittivity. Is it clear? Right. So already I said you this one. Okay. K in terms of force, K in terms of electric field. Now K in terms of electric potential is this one. Okay. Ohm, I said you the trick also. How to remember this one? This is what? Force in free space upon force in medium. Electric field intensity in free space upon electric field intensity in medium. Electric potential in free space upon electric potential in medium. Is it clear, beta? Remember, beta, please remember, don't get confusion. Okay. Already you have solved the numericals, you know the concept also, but now what you are learning here is what are the key points which I have to remember. That key points I am teaching you now. Okay. Please remember, this all are key points. Okay. Note down in your book. Okay. Chalo. So K is equal to F0 by Fm. Okay. The trick how to remember this one? Ohm. Right? Om. Ohm. 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 Is it clear, beta? Clear na? So this is also one trick for you. Okay. Right. See here. Only for one charge. If there is only one charge, he will be asking you in exam, calculate the electric field, or else he will be asking you, calculate the electric potential due to this charge. Clear? Right. So if there are two charges, 100% he will be asking you the calculate the force between these two charges, or else he will be asking you to calculate, find the potential energy present between these two charges. Is it clear, beta? Chalo, no more confusion na? So now see here. Now let us see the graph for this one. Okay, electric potential and the distance. How they are, beta? Electric potential is inversely proportional to distance. Correct? Inversely proportional. As the distance increases, of course, this decreases. Na? Inversely proportional relationship, as everyone know that one. Okay. Inversely proportional graphs. How you will get? Of course, like this you will be getting. Is it clear? This is the inversely proportional graph, beta. Okay. No more confusion, na? Right. So don't skip the class. Listen carefully. Note down each and every point. Okay. These are 100% helpful for your NEET as well as JW. Okay. Electric potential. See here. Electric potential formula is what? KQ by R. This formula, when we have to use? This formula is applicable for point charges. Okay. This is what scalar quantity. SI units are volt, volt. Okay. For positive charge, it is kq by r. For negatively charged, minus kq by r. Okay. Right. So V equal to kq by r. K value is what? I said you 1 by 4 pi epsilon naught into q by r. So K value is 1 by 4 pi epsilon naught. That value is 9 into 10 power 9. Right. Now, note. This is a very important note. Based on this note, you are able to solve so many numericals which you got in a previous year. Okay, so many questions you have, beta. Okay, so just I will be explaining you one point. Okay, if this point clear for you, definitely you are going to solve the numerical, because right now I can't take the numerical for you. Okay, I said you know to complete this one chapter, it takes nearly about 10 to 12 hours. Okay, so just key points I am telling you, just remember these points. Okay, 100% you will solve the numericals within seconds. Okay, less than 1 minute you are able to solve better. Okay, now see here, remember this one. If a charge is moving in step 1, so first listen here. This is the step 1. Okay, so these steps are in circular shape. Okay, so this is the first step, and next one. Okay, and next one. Okay, like this, like a stage. Okay, like stage, cricket stadium. So the steps will be like this, on inclined. In the same manner, you have step 1, step 2, step 3, step 4. Okay, so you can take the example of this one also. So if you go to the ancient temples, okay, you will be finding there. Actually, we call in Telugu as a konero. Okay, so the water will be present over here. Correct? You will be going there. You will be taking bath there. Next, you will be going for the darshan. Correct? Yes or no? I think you got the point, right? In pictures also they will be showing you now, beta. Yes. So here is the water. You will be coming like this. Okay. You will be so taking the water and you will be pouring on your head. And next you will be going for the darshans, right? Yes or no? You got the point, no? Now listen carefully. Listen carefully. So you are in step 1. Okay, you are in step 1. Okay, actually these surfaces are called as equipotential surfaces. Okay, so these surfaces are called as equipotential surfaces. You will be getting later that one. So chalo. So I am explaining this one as a roughly for you. Okay, but 100% these are 100% helpful for you to solve the numericals. Okay, now so you are able to move in step 1 easily, no problem for you. Okay, no need of doing any work, no need of doing any work. Okay, when you are moving in a step 1. Okay, this complete step 1 belongs to you only. Is it clear? This complete steps belongs to you. No need of doing any work. Okay, right. So your friend is in step 2. So this step 2 belongs to him. Okay, so wherever he go, no problem for us. Okay, in step 3 another friend you have. Okay, so he is moving in a step 3, no problem. This complete step 3 belongs to him. Okay, like the same manner step 4 also. Okay, now when you will face the problem is when a person is moving from step 1 to step 2 or else step 2 to step 3, at the time work is said to be done. At the time work is said to be done, beta. Okay, see here is a charge I am taking capital Q. Okay, here is a charge I am taking capital Q. In questions he will be asking you like this. Okay, so there is a charge capital Q and there is a one more charge which is Q0, which is at a distance of small r. Now he will ask you the question like this. Okay, find work done for bringing for rotating a charge. Find work done for rotating this charge in a circular path. What is the work done? You are rotating this charge in a circular path. Okay, here in this case the external work done, no need of doing any work, beta. No need of doing any work here. Okay, no need of doing any work. Why? Because this total circle belongs to you. Okay, this total circle belongs to you. No need of doing any work. Okay, even he may ask you the question like this also. Sir, in first case, I have bought this charge from here to here, and next case here, and next one is here, and next one is here. Okay, in which case the person has done more work? In which case the person has done more work? So you'll be thinking that, sir, this is like a straight line, na? Okay, this is like a straight line. In this case, the work done is more. You'll be writing here. Okay, but it is a wrong answer. Wrong answer. See here, that is a wrong answer. Why? I'll tell you. I'll tell you. I said you know this complete circle belongs to you. Correct? So delta V is equal to, he is asking about the work done. I said you in the beginning. Based on this formula, you will be getting the questions. Okay, Q. So now, delta V is what? Final minus initial. Finally, where it is reaching? So in this case, VA minus initially where the charge? It is at point O. Okay, so O to A. Work done from O to A for bringing a charge small q. Clear? What is the potential at point A? KQ by R. Correct? KQ by R. What is the potential at point O due to this charge? Again KQ by R. O to A. Am I right? KQ by R minus KQ by R. Finally answer is what? 0. No need of doing any work. Okay, so many questions we have, beta. But I can't explain you the questions here. But I can tell you the key points, what exactly you have to remember. Is it clear? I hope you have understand my concern, what I am going to tell. Okay? Right, beta. So, see here, if a charge is moving in a circular path, what is the external work done? No need of doing any work. 0. In this path, 0. When work is said to be done? When a charge is moving from one step to another step. Okay? Like this. Up to down or down to up. Okay? In that case, work 100% done, beta. Okay? So, work done, he is asking na, use this formula. Okay? Delta V is what? Final minus initial. Okay? Finally, where you are reaching, check that point. Initially, where you are, check that point. Is it clear? Right, beta. If a charge is moving in step 1, then there is no work done. Okay? If a charge is moving from step 1 to step 2 or 2 to 1, then work is said to be done. Okay? 100% you will get an answer here. Okay? Is it clear? From here to here you are moving. I am taking the charge. Okay? I am bringing the charge from this point to this point. 100% work done. Distance is different. Is it clear, beta? I hope you got my point. Okay? Chalo. So let us go further. Okay? Note. Remember this one. This one. Oh my God. This one is very infinite times important, beta. Okay? Infinite times it is important. If you know about the work energy theorem, definitely you are going to solve all the numericals. If you don't know that one, work energy theorem, of course you will be facing definitely problem better then. Okay? Right. See here. Work done by external by charge Q equal to delta V, as everyone know this one, correct? Work done by external is equal to minus work done by conservative. Okay? Work done by external is equal to minus work done by conservative forces. Okay? In place of work done by external, I have written this one. That's it. Equal to delta V. Okay? What are the conservative forces? Okay? What are the conservative forces? Electrostatic forces, spring forces. Okay? So GEMS. So like this you can remember. The gravitational force, electrostatic force, spring forces, all are the conservative forces. Okay? Here we have electrostatic forces now, charges. Okay, electrostatic forces are nothing but what? Force. The force which is present between the charges is called as electrostatic forces. Okay? If you don't know anything, just remember this formula. Okay? Just remember this formula. Okay, 100% you are going to solve the numericals. Okay, chalo. So yeah, if this is a regular class, really you are going to rock the classes. Each and every class you are going to rock, beta. Okay, um, chalo. So see here, work done by external equal to minus work done by conservative, that is equal to change in potential energy. So this formula is very important. I will tell you the importance of this formula. So uh, it will be help you like a Brahmahastra in your exam. Okay, so I think you heard about the Brahmahastra, right? Bow and arrow, the Arjun has a Brahmahastra. He used to use that one, correct? So this formula is like a Brahmahastra in your NEET as well as in JW exam, beta. Okay? Chalo, right. Please note initial and final points. Okay? Here delta V you are using na. Finally, where your final minus initial. Okay? Please note down. And in questions, he will be mentioning the points also, where to where you have to do the work. So just to note down the point, sir, from here to here, you have to do the work. See here, so this is a capital Q charge, which is kept at a 10-meter distance. Here is a small Q naught, okay, which is at point A. What I have done is, I have taken this charge, I have brought here, okay, from here to here, from here to here, I have done a external work, I have left here, I have put it here, okay, I have taken the charge from here, and next I have put it here, okay, take the charger here and next put down here. Is it clear, beta? So what is the external work done? Find the external work done for bringing a charge from point A to point B. External work you have to calculate. So to calculate this one, which formula you have to use? Potential. Your delta V is equal to external work done from A to B is upon for Q naught, na? Okay. So this is what? Final minus initial. Finally, where we are reaching B. Initially at point A. So external work done A to B by Q naught. Okay. What is the potential at point B? What is the potential formula? KQ by R. K into capital Q by, okay, so this with 2 meters. Okay. So what is the final distance here? Now it is 12 meters. No? KQ by 12 minus KQ by initially it is 10. Khatam. You got the answer, beta. Okay. So finally send this charge here and calculate this one. That is the final answer. Okay. So this is the amount of work done you have. So this is the amount of work you have done for bringing a charge from point A to the point B. Is it clear, beta? So like this you have to solve the numerical. There are so many numericals, but I can't help you now. Okay, but I can help you regarding the key points and the remembering point, and for doing the reasons, these are helpful for you. Okay, chalo. Now next, electric potential due to circular charge wire. Okay, so see here, this is a wire. Okay, so just add some charge on it. Is it clear? Let the radius of the wire is capital R. Okay, and what is this one, beta? This is the axis. Okay, right. At this point, you have to calculate the potential due to this circular charge wire. Okay, yes, beta. So from here to here, so what is the distance from here to here? It is taking, I am taking as a R, beta. Okay, so you have to remember this formula, beta. The potential due to the wire. Okay, what is that one? So in the last class, in electric charges and fields, we have calculated the electric field intensity on the axis, right? So what you got here? KQR by capital R square plus small r square whole power 3 by 2 you got, right? What is the electric potential due to same thing? Same ring. What you get, beta? KQ by under root of capital R square plus small r square. Okay. What is the potential at the center? KQ by R. Okay. What is the potential at the center? Center is nothing but this point. Okay. This point is shifting to here. So R becomes 0, na? So put down the R becomes 0. So finally what is left? KQ by R. Is it clear? Sir, electric field is 0, na? At this point exactly it is 0. Okay. It is 0. 100% is 0. Sir, even electric field is not present, then potential will be present. Yes. Yes, it is present. Okay. So this is an example for you. Yes? Electric field intensity is what? At the center. It is 0. What is the electric potential you got? KQ by R. Is it clear, beta? Okay. Now see here. Potential due to disk on the axis. So disk is nothing but, so here we have to take the surface charge density. Okay, surface charge density. Surface charge density is denoted by symbol sigma. Okay, this is a radius capital R. Okay, so from here to here, small r, small r I am taking. Okay, at this point you have to calculate the potential. Okay, so by using the Pythagoras theorem, what you get? Under root of capital R square plus small r square, right? So just potential at point P. Just remember the formula. It is sufficient. Okay, sigma is what? This one is what? Areal charge density. It is what? Areal charge density. What is it formula? Total charge by total area, small charge by small area. Is it clear? Yes. Now, see here, I have forgot to write here plus. Okay, Pythagoras theorem beta, that one. Okay, so easily you can remember now. Remember all the formulas beta, they are the imported formulas. Based on these formulas, you are going to solve the numericals. Okay, the change in potential, concept based question you will be getting there. Okay, delta V is equal to work done by external upon Q. Is it clear? Remember that one. Okay, the potential always remains constant. When radius is constant, they are called as the equipotential surfaces. Okay, there is no need of doing work. Already I have explained you one question, a small question I have taken. Okay, see here beta. Charge distribution. So first one is a one dimension. Lambda is called as a linear charge density. Okay, so I have taken my hair. Okay, so let us assume that in my pocket there are so many charges present inside that one. Okay, so what I am doing is I am doing like this. Okay, right beta. So I am dipping inside. I have taken out. What happens? Sir, the charge is distributed on this hair, right? So now this is what? One dimension. So what is the charge? Total charge present on that one? Q. The length of the hair is L. Total charge by total length, small charge by small length. Okay, now the 2D, two dimensions are what? Paper. Okay, so I have taken a paper, this much small size paper. Okay, a rectangular shape paper. Okay, so that is a two dimension. Next, what I have done? So I have dipped this paper in my pocket so that of course the charge will be distributing on the surfaces, this surface and this surface also, right? So there you have to call the areal charge density. Okay, that is called as areal charge density, denoted by symbol sigma. Total charge by total area, small charge by small area. In the same manner, okay, volume charge density. Acha, is it not? This one is rho. Okay, rho. So in the same manner, total charge by total volume, small charge by small volume. Okay, remember the formulas. Right. Relationship between electric field intensity and electric potential. Okay, now very important. Based on, if you remember this formula 100%, you are able to solve the numericals better. Okay, now see here, for a positively charged, as the distance increases, see here, as the distance increases from the charge, the potential goes on decreases. Okay, here, see here, this is a 50 volt. Let us assume that. So wherever it may be. Okay, so any, you see here on this surface. Okay, on this line, on this circle, anywhere it's 50 volt only. Is it clear? What is the potential on this one? It is 50. Okay, what is the potential here? 40. What is the potential here? It is 30. Okay, for a negatively charged, the potential near to this one. Okay, so this one has a 30 and this one has a 40 and this one has a 50. Okay, so from here to here, this goes on decreases. Is it clear? But for a negatively charged, that is for positively charged. So these surfaces are called as what? Equipotential surfaces. Okay, equipotential surfaces. The potential is equal on the surface. That's why they call that as a equipotential surfaces. Okay. These are the important, okay? Remember the formula. E is equal to minus dV by dr. Okay, so remember this one beta. For a single charge, what you have, sir, we have electric field intensity and electric potential we have. The electric field intensity is kq by r square and the electric potential is kq by r. Correct? Am I right? Yes. So for a single charge you have electric field intensity and the electric potential. Now we are finding the relationship between these two, electric field intensity and electric potential beta. Okay. Now E equal to minus dV by dr. So this formula, when you have to use this, when potential is variable, you have to use this one. Delta V equal to integration of E into dr. When you have to use, when electric field intensity is variable, delta V is equal to E into delta R. When electric field intensity is constant. If theta is present between electric field intensity and R, then E cos theta into delta R beta. Okay? E cos theta into delta R. Now see here, note down. See here, electric field is in this direction. Okay? Okay? The distance is in this direction. Okay? So so let us calculate the electric potential between these two. Okay, electric field intensity is here. Let us take as a constant value. Okay. So if electric field intensity is constant, just now I said you, what is the formula? Delta V is equal to minus E into delta R we have to use, right? Electric field is always taken along the direction of distance. Electric field is always taken along the direction of distance. Okay. So this is E. Wherever theta is present, there will get what? E cos theta. Is it clear? E cos theta into distance is what? R. So like this you have to solve beta. Okay. Is it clear? There are so many questions also. I can't take the questions now. Okay. But I can cover the important points. Okay. I hope please understand better. Okay. Chalo. So if you already you have learned this chapter from your teacher, right? In institutions, in classes also you have learned this, all the things. Okay. Only I am covering the important points. Sir, after watching the video, I am unable to understand the class, sir. So it's not your mistake, beta. So actually, I am taking only the key points. If I take with the numerical, definitely you are going to rock that one. But only this is possible in regular classes only. Okay, because it takes a lot of time. Okay, in that time detail is small. Okay, slowly I used to explain this all the things. Is it clear, beta? Chalo. So let us go forward. Okay. See here. For positive charge, the graph beta, potential versus distance. So graph like this. For negatively charged, so you'll be getting like this. Is it clear? Next, potential due to conducting and non-conducting charge spheres. For conducting sphere, charge will be present on the surface, right? The charge will be not present inside the sphere. Okay. In non-conducting sphere, charge will be present inside as well as outside also. Am I right, beta? The main thing what you have to remember is, I'll tell you. Okay. So charge is present on the surface as well as inside also, right? So see here. So at this point P, you have to calculate the potential due to this conducting sphere. Okay, the charge on this one is Q. Of course, everyone know that the radius of the shell is R, capital R, and from here to here, in the last class I said you that taken as a small r, correct? In the last class, electric charges and field, I have explained you this concept, right? There we have calculated the electric field intensity also. Now we are calculating the electric potentials here. Okay, chalo. So electric potential outside, what you get? Kq by R, normal formula. Here also normal formula, Kq by R. Electric potential on the surface, of course everyone know that small r is equal to capital R. In place of smaller, keep capital R. Here also same thing. Now potential inside, Kq by R. Sir, electric field intensity inside we got 0 because no charge, but electric potential we got, na? Actually there is a proof beta, so I can't explain you now. Okay, please understand. So electric potential at the center, of course, KQ by capital R only. Okay, KQ by capital R only. Electric field intensity at the center, again we got the zero, na? In the last class I taught you, correct? Is it clear beta? Write down each and every point, this one, okay? Please remember all the formulas beta. These are the very important formulas. Okay, if you do revision this chapter, it is sufficient for you. Okay, chalo. So each and every trick, concept, which formula, where to use, when to use, I'm explaining you this, all the things for you, right? So listen carefully, do the revision and remember all the things till NEET exam or JEE exam, till board exam also. Chalo. See here beta, now in this case, what is the potential inside is this one. So this formula is very bigger. So somewhat you have to remember. 99% in NEET and JEE, he will not ask you. Okay, rarely he may ask you. Okay, this one he may ask you. Okay, this one is he may not ask you. Okay, but the thing is you have to remember that formula. Okay, potential inside the non-conducting sphere. Okay, right beta. So potential at the center is what? 3 by 2 times of potential on the surface. KQ by R is what? Potential on the surface. 3 by 2 times it is bigger beta. Okay, now so I'll show you the diagram. Okay, so here is a, see here, potential versus distance graph I am drawing here. Okay, from the center, potential versus distance. Okay, this is what, sir, this one is small r equal to radius, na? Correct. Sir, this one is small r equal to radius, correct. Now tell me beta, what is the potential at the center? Potential at the center, KQ by capital R. So let us assume this one is a KQ by capital. Okay, KQ by capital R. Is it clear? Sure. Inside KQ by capital R or not? Inside KQ by capital R only, na? Next, on the surface KQ by capital R only. Okay. Chalo. Next, outside KQ by small r. Outside we reached. Potential is inversely proportional to small r. Inversely proportional graph, everyone know na? Potential is inversely proportional to r. 99% he may ask you the graphs only. 99% chances. Okay, 99% he may ask you regarding this graphs. Okay. Next. So here, potential at the center, 3 by 2 times of potential on the surface, na? So 3 by 2 times of KQ by R, correct? So here at the center is this one. Okay, now next, inside, it is inside, na? So somewhat you will be getting like this beta. Okay, somewhat you will be getting like this. Okay, on the surface, this is what? On the surface, KQ by R you have reached. Okay, outside is what? Inversely proportional, right? Inversely proportional graph you will be getting like this, correct? So you can identify from the graph. Okay, so you'll be giving you the graphs now, so easily you can identify that one. This is 3 by 2 times of potential on the surface. Okay, this is on the surface. Next, like this you'll get. Is it clear? Just remember the graphs. Now, V versus graphs. V versus R graph in conducting and non-conducting charge spheres. Just now I shown you. Just draw the graphs here. Okay. Electric potential due to dipole on the axis. As everyone know that this is a dipole, right? Small r is always taken from origin only, correct? So axial line, this is called as axial line. Okay, the distance separated by them is 2L. Is it clear? On the axis, what is the formula you will get? Kp by r square. Kp by r square. So what is the P? Indicate dipole moment, correct? What is the formula? Q into 2L. Okay, electric dipole moment it is called. Okay. What is the electric field intensity on the axis? What you got? 2 Kp by r cube you got, correct? In the last class you got. Chalo. So potential is this one, Kp by r square. Okay. So electric potential due to dipole on equatorial line. Equatorial line is nothing but this one. Okay. So here you will get is 0 beta. Electric potential, what you get? 0. So what is the electric field intensity? What you got beta? Kp by r cube you got. Correct? Kp by r cube. Electric field intensity you got this one. That is the electric potential. Okay. If any one of them you know, you can calculate the other. Correct? Because I have given you the relationships. Correct? Relationship between the electric field intensity and electric potential is equal to minus dV by dr. I given you. Okay. Electric potential at any point in space. What you got? Kp cos theta by r square. Kp cos theta by r square you got, right? Sure. So for this one, electric field intensity at any point in space, what you got? Kp by, so cross check, you can cross check that one. Kp by r square under root of 3 cos square theta plus 1 you got, correct? Kp by r square under root of 3 cos square theta plus 1 in space you got, correct? Sorry, Kp by r cube. Correct? Kp by r cube under root of 3 cos square theta plus 1. Okay, you can cross check that one from the earlier chapter. Okay. Potential energy due to system of charges. Okay. I said you now, if there are two charges separated by distance small r, then the potential energy between these two is what? K q1 q2 by r. Okay, this is what? Scalar quantity. Is it clear? For two charges, if there are two charges, 100% you will be getting one force, K q1 q2 by r square, and one is a potential energy you will be getting, K q1 q2 by r beta. As everyone know na, K value is what? 1 by 4 pi epsilon naught. Okay. Now, potential energy in terms of dielectric, okay, or relative permittivity. So what is that one beta? Already I said you, for force ohm, electric field ohm only, potential also ohm, potential energy also ohm. Is it clear? Remember this one. He may give you this one, so you have to calculate this one. Clear? Sure. Note. So here, buy one get one free. So not that much, so much different. See here, let it be. Note, remember this one, as here we are discussing about the potential energy, na, delta U. As we know that work done by external equal to change in potential energy. Yes, work done by external is what? Minus work done by conservative also. Okay. So most if you remember this one, it is sufficient beta. Work done by external equal to minus work done by conservative equal to change in potential energy. Okay. Remember this one. Very important. Okay. No points we have only system here. In potentials, delta V is equal to work done by external by Q na, there we have to look at the points, but here you should not. Is it clear beta? Okay. Chala. So dielectric, what is dielectric? Dielectric are insulating non-conducting materials which transmit electric effect without conducting, only transmit the electric field, correct? Right. So dielectric are of two types. What are they? Non-polar and the polar dielectric. This is important for your board exam. So whatever the points I have written here, just copy and paste there in your board. Okay. 99% you won't get in JEE and okay, you won't get in JEE and NEET also. Non-polar. So just go through this one once. Okay. Non-polar dielectrics. So they are not polar. See here they mentioned here non-polar. So no dipole moment. No dipole moment. That's it. Okay. The molecules in which the center of positive charge coincide with the center of negative charge are called non-polar molecules. Okay. Such molecules are symmetric in sphere. Example, this all the thing. But the dipole moment 0. Correct? Because See here, center of positive charge and center of negative charge coincide here, as center of positive charge coincide with the center of negatively charged. Is it clear, beta? Dipole momentum is 0. Polar, here you have a dipoles, okay? The molecules in which the center of positive and negatively charged doesn't coincide because of asymmetric shape of molecule are called as polar molecule. Here you have a net dipole moments. Here negative charge, positive charge, dipole moment direction always from negative charge to positive charge. Everyone know this one, okay? So here also negative to positive, net resultant you will be getting in this direction, correct? Now, dielectric polarization. See here, when a non-polar dielectric is held in an external field. So in the beginning, I am taking the non-polar dielectric substance. Later, in the next slide, I will be taking the polar dielectrics. Okay, I will be keeping in an electric field. Okay, first is a non-polar I am taking and keeping this one in an electric field. Okay, is held in an external electric field E naught. Okay, non-polar electric field. Okay, see here. So based on the diagram also you can conclude this one. So here there is no dipoles here, na? Yes, if the external field is applied, so they will be getting separated like this. Okay. Chalo. So see here. E naught, the center of positive charge protons in each molecules is pulled in the direction of the electric field, and the center of the negatively charged electron is pulled in the direction of the opposite to the electric field, correct? Because here you have a positive charge, negative charge, na? So when you keep this one in electric field, what happens? Positive, positive, get repel. Positive, negative, get relaxation. This is what positively charged plate. So here you'll be getting the negative. Okay, this is what negatively charged plate. So here you'll be getting the positive. Is it clear? Chalo. So then molecules are said to be polarized. After keeping this one, a non-polar molecules, after keeping in electric field, they get polarized. Okay. Now, when no external field is applied to a dielectric with a polar molecules, then different permanent dipoles are randomly oriented due to thermal agitation, so that total dipole momentum is 0. See here, in the beginning, non-polars, there is no dipole moment. But here, I am taking the polar molecules now. Initially, they have a dipoles now. Yes, so in the absence of electric field, of course, they will be having a random direction. The net we consider as a 0 only. After keeping this one in electric field, okay, they will be arranged in an order. Okay, chalo. When an external electric field E naught is applied, the individual dipole moment tends to align with the field. When summed over all the molecules, there appear some net dipole moment in the direction of the external field. Hence, it is polarized. Is it clear, beta? This is a very simple and dead easy, na? So you can learn this one also. Okay, no need of explanation also here. So it is found that the electric polarization is directly proportional to the effective electric field, okay, in a polarized dielectric. Okay, see here. So this is what external electric field, correct? So inside this one, what will get induced? Okay, so due to this one, some induced electric field is produced inside this one. Okay, here are all the positive charge, here is a negatively charged. So from here to here, okay, so the induced electric field we called it as, okay, due to the polarizer, okay, due to the polarization. Is it clear, beta? Sure. So dipole moment direction is what? This direction. Okay, negative charge to positive charge. No? These are the negative, this is the positive, like this they are going. Okay, right, but just remember this one. This is important only for the boards. Polarization is directly proportional to external electric field. If you remove this one, we get a constant susceptibility. This is zeta, susceptibility of the dielectric. So here polarization is nothing but what? Net polarized. Okay, net dipole moment upon volume. Okay, the electric susceptibility describes the electrical behavior of the dielectric. If zeta equal to 0 for vacuum, effective electric field is polarized. Dielectric is net electric field intensity is what? External is going in this direction. Okay, induced is coming in this direction. E naught minus EP. E naught minus EP net. Is it clear? Note for metals, E becomes what? 0. Net electric field intensity will become what? 0. Already, I hope you have solved the numericals, right? A charge we have to take here, and a spherical spheres. They are close. One more spherical sphere is enclosed, and one more is enclosed. So you have to distribute the charges. How the charges are distributed? I think you have solved the numericals, right? So see here, charged spheres always. What happened, beta? Doesn't. Metallic spheres. Metallic spheres. Inside the metallic spheres, electric field is always 0. Yes or no? Yes. Chalo beta. So let us go. Next capacitors. Okay, so this is a very important, as everyone know. Maximum you will be getting the combination of capacitors, beta. Okay. See here, what is a capacitor? Energy stored device. Large energy is released at once. Generally we call that as capacitors are what? Energy stored devices. Okay, what they will do? It will release the energy at once. Large amount of energy at once. Like a bomb blast. Okay. SI units are farad. Dimension formula I have written. Okay. See here, capacitance formula is what? C equal to Q by V. Most of the students used to tell that, sir, C depends upon Q and C depends upon V. Really, C doesn't depends upon the C doesn't depends upon Q and V. It doesn't depend. It depends upon the dimensions. Okay, these are the key points. Just remember. Okay, capacitance of spherical shaped capacitor. This is a spherical shaped capacitor. C equal to, as everyone know, this is a formula. Okay, potential due to the surface, as everyone know, KQ by R, right? So Q equal to what you got? This one you got. Just substitute the Q value and put it here. You will get this one. Okay. Now see here, beta. 4 pi epsilon naught R you got. Okay. I said you na, the spherical shape capacitor. Capacitor depends upon the dimensions, not upon charge and potential. It is depending upon the radius. Okay. C depends upon the radius. Okay. Radius of the sphere. Now, energy stored in spherical capacitor. Just remember, based on this formula, you may get a question in your board as well as in JEE also, in NEET exam also. Okay. Based on this formula, direct formula based question. Energy stored in capacitor, half CV square, Q square by 2C, half into Q into V. Wherever capacitor you have observed, 4 pi epsilon naught R. Just substitute this value. Okay. If we mentioned spherical capacitor, okay, what is the energy stored in spherical capacitor? Half CV square. In place of C, write down this one. Katam. Finished. Okay. Parallel plate capacitor. This is a positive charge. This is a negative charge. The distance separated by them is small d, and the area of cross section of this one is capital A. Capacitance. I said you know, C equal to Q by V. It doesn't depend upon Q and V. It depends upon dimension, the distance separated by this one and the area. Okay. Formula is epsilon naught A by D. Remember this one. Okay. Right. So energy stored in capacitor, parallel plate capacitor now. Parallel plate capacitor. Same formula. Okay. For the spherical shape capacitors, energy stored, and parallel plate capacitor, energy stored. Same. In place of C, write down here epsilon naught A by D. In case of spherical shape capacitor, in place of C, write down 4 pi epsilon naught R. That's it. Next, force between two parallel plate capacitor. Okay, there are two parallel plates now. What is the force between them? This one is a force. Sigma is what? I said you na. Parallel plates. Okay. So what you get? Plus sigma. And next one is minus sigma you will get, right? Yes or no? Because aerial charge distribution we have to take. Okay. So this one is sigma into q by 2 epsilon naught. Okay, sigma into q by 2 epsilon naught, or else you can write down q square by 2 epsilon naught. You can write down this one also. Okay, just remember beta, that's it. Distribution of charge. Okay, when two charged bodies having a charge q1 and q2 having a different radiuses, okay, when these two are joined by a wire, okay, what happens at that time? Charge gets shared down. Till when it will be shared down? Until they become the common potential. Okay, until you get a common potential, the charge will be sharing down. What is the common potential formula? This is a trick, remember. Okay, direct question. Next, distribution of charges. Okay, now see here in the same case only. See here, just now we have observed this is the charge q1, this is a q2. Okay, like this we have taken. See here, so after charge distribution, some final charge will be left on q1, correct? Next, some final charge will be left on q2 also, correct? What is that one? Okay, so the final charge left on q1 be q1 dash, so c1 into v common potential. Okay, common potential formula you know, just now I have written q1 plus q2 by c1 plus c2. Okay, charge left on q2, c2 into v common potential. Okay, during this process some energy will be lost here. Okay, what is that lost energy? Half c1 c2 by c1 plus c2 into, in bracket, higher potential minus lower potential. Okay, higher minus lower potentials. Chalo, series combination of capacitors, as everyone know. Okay, this is a series connection. Here are the potential drops, these are the capacitors, this is the potential I have applied. Okay, in series connection, charge always remains constant, potential get drops, correct? So here what you will get, effective capacitance 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3, correct? If there are only two capacitors, use this formula beta. Okay, if there are only two capacitors, use this formula. Don't use this one, 1 by C effective equal to 1 by C1 plus 1 by C2. If you use this one, it takes somewhat time to solve the numerical. If you use this one, okay, it takes less time to solve the numericals. Okay, so for n same capacitor, C effective becomes C by n. Remember this one. Okay, in the same manner, series combination of resistance, series combination of capacitor finished. Now series combination of resistance. So this one you have learned, right? Series combination of resistance. Okay, in series combination, here current always remains constant. We use the formula V equal to IR. In capacitor, we use the formula C equal to Q by V, correct? Chalo. So voltage drops across each resistance is V1, V2 and V3. Okay, effective resistance become direct addition. Okay, for n same resistance it is NR. Now parallel. In parallel combination, we have to keep the capacitor, okay, below of that one. Okay, chalo. So here we are supplying the voltage V. From here the charge is going here. Okay, so after going here, what is happening? Okay, so till here it is no problem. After reaching this point, what happens? It absorbs the three ways, correct? So some amount of charge will be going here, 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 right? In three ways charge will be distributed. Is it clear beta? Okay, take the, so see here beta, this is very simple. So this is a pipeline. Okay, so water is going like this, like this, like this, like this, till here the water went. Okay, what happens now? Here there is a one joint here, right? The water supply will be moving in this direction, in this direction and in this direction in a small amount, right? Khatam, that's it beta. Here C effective becomes C1 plus C2 plus C3. For n same capacitor it is NC. Okay, in parallel combination potential remains constant, charge becomes change. Okay, charge will be different. Okay, yes beta. So parallel combination of resistance. In parallel combination also voltage remains constant, as well as in parallel combination of capacitor voltage remains constant, correct? Okay, so in capacitors we take the charge, In resistance we take the current. Okay, chalo. So potential remains constant, current changes. Effective resistance become this one. If there are two resistance, use this formula, R1 R2 by R1 plus R2. For n same resistance, use R by n. Okay, based on this one only you are going to solve so many numericals. Okay, key points. Now see here, combination of capacitors. So in series combination, if there are two capacitors, C1 C2 by C1 plus C2, for n same capacitors it is C by n. In parallel, if there are two capacitors, direct addition, for n same capacitance you have to write NC. Okay, when battery is connected and removed, these are the very important beta. Okay, so many previous year questions you have on this topic. Battery connected and removed. So during this process 100% charge remains constant. Keep this one in your point. Okay, note down this one. When battery is connected, its potential energy will be very high. Okay, when charge always remains constant, remember this one. Okay, when battery connected and removed questions. Okay, when battery is replaced by another capacitor, at that time potential energy becomes low. Okay, the effective capacitance changes. Potential, which potential we have to take? Common potential we have to take. Okay, initially we have somewhat another potential. Okay, after joining here, see here beta. So this is a potential V, this is a capacitor C. What is the potential energy now here? Q square by 2C, correct? Now the charge has been stored there. Next, what I have done? I have removed this one. I have replaced it with another capacitor. Okay. What happens? Charge will be distributed equally until they become the common potential. Okay. Okay. Is it clear? Right. So here the potential energy formula, one more formula you have. Which one? Half into Q into V. Half into Q into V. Correct? Yes or no? Here you get what you get. Here you have a potential V. Here you will get the common potential V. That's why I have written a change. That's it. Okay. Is it clear, beta? Okay. So common potential you will be getting something. Okay. Now the final potential energy. So which one you have to use? You have to take the charge Q. Q in V terms. Okay. Half into Q into V. Half into Q into V common potential. So you have to use this formula. Final potential energy, initial potential energy, common potential. Something you will get na. What is that one formula? Q1 plus Q2 by C1 plus C2. Q1 plus Q2 is what? Total charge always remains constant. Q by C1 plus C2, C plus C2C. Okay, like this you have to solve the numericals beta. Okay. Chalo. So during this process, I said you na, in battery connected and removed, charge remains constant. Remember, after sharing, charge left. Okay, so what is the charge left is what? So Q dash equal to V common potential. Okay, in bracket Q1 plus Q2. Here, this one. See here, beta. Just now I said you know V common potential. Charge is distributing. Am I right? Yes or no? First you have connected the battery. Capacitor has fully charged. Now you have removed this one. Okay, now you have replaced with another capacitor. Yes, right. Now, so finally what you will be getting better here? The charge will be distributed, right? So till what time it will be distributed? Until they get the common potential, right? Until they get the common potential, charge will be distributed, right? So V common, after distribution of charge, what is the final charge left? I said you know V common potential. Okay, into C1 here. Okay, V common potential into C1. Here V common potential into C2. Is it clear? Q2 dash. In the beginning I said you know the same question beta. This one, two charged bodies we have solved na? In the same like this connection we have taken na? Here also the same thing. Here also the same thing. Okay, this is a C1 and this is a C2. What is the final charge left here? This one. Is it clear? Okay, chalo. So this one has been cleared. Okay. Distribution of charge on plates. So like this question you have observed, I think so, right? So we have to find the distribution of charge on these plates. Okay. So for this one, there is one trick, beta. Okay. Charge on the surfaces is equal to sum of the charge divided by 2. Okay. Add all the charges. 3q plus 2q, 5q, 5q minus q, 4q, 4q by 2. So what is the, you got 2q, na? First what you have to do is, write down the 2q here and 2q here. Okay, on outer surface, first and last, outer surfaces. You have to write down the 2q, 2q. Okay. Next. So what is the total charge on this one? 3q, na? Already 2q is present. So 1q is left. So write down the q here. Okay, as everyone know that this inside the parallel plate capacitor, charge should be equal but opposite, right? If this is q, 100%, this should be a minus q. Okay. Now tell me, what is the charge present on this one? It is 2q. Already minus q is present. Okay, so write down here 3q. 3q minus q, 2q. You got it? Yes, beta. So as inside the parallel plate capacitors, the charge should be equal but opposite. If this is 3q, this should be 100% minus 3q. What is the total what is the total charge present on this one? Minus q. In order to present minus q, how much charge should be present here? 2q only, na? Already we have written in the beginning. Now cross check. Minus 3q, 2q, q. Hence proved. Okay. Chalo beta. So this is the best trick to solve the distribution of charge. Okay. Potential method. As everyone know, no? Potential method, how to solve this one. So you have to calculate the effective capacitance here. Okay. Right beta. So see here. At point A, potential, we have a higher potential. Okay. Charge always flow from a higher potential to lower potential. Okay. So here is V. Till here it is V only. At point B, we have a lower potential, that is O. Nahi to 0. 0 potential, 0, 0, 0, 0. Till here it is 0. Right. Now what you have to do is, so write down the first A here and next here B. At point A, you have a higher potential. At point B, you have a lower potential, right? Am I right? Okay, write down like this. Now, in between V and O, there is one capacitor. Okay, in between V and O, there is one capacitor. Finish. In between V and O, one more capacitor you have. Okay, chalo, finish. In between V and O, one more capacitor you have. Okay, so finally, these three are in parallel. So final answer is what? 3C. Is it clear, beta? Is it clear for everyone? Okay. Chalo. So like this you have to solve. In parallel connection, directly we'll add, na? Okay. Now, so Wheatstone bridge condition. So what is this Wheatstone bridge condition is? I'm taking the capacitors here, okay, which is in this shape. Let us assume the capacitor name is P, Q, R. Acha, this is R. Okay, and this is a S. Okay. Now, if P by Q equal to R by S, condition for the Wheatstone bridge is what? P by Q equal to R by S, then 100%. T becomes 0. So I'm taking one more capacitor in between these two. Okay. So at that time, okay, so we have to remove that one. We have to remove that capacitor, beta. Okay. No charge flows across that one. We have a proof also, but no need. No need. Is it clear? Chalo. So let us go next. Mirror symmetricity. As everyone know the mirror symmetricity. Okay. To calculate the complex numericals, we use the mirror symmetricity and folding symmetricity, beta. So by using the mirror and folding only, we are able to solve the numericals. If you don't know this one, of course, the complex numericals, a single question also, you are unable to solve this one, beta. Okay. Yes. In mirror symmetricity, see here. So this here it is 2C, 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 2C. Okay. What I am doing is I am taking a mirror and keeping over here. Okay. Right. So here it is 2C. In mirror, it will be looking 2C only, no? Here it is 2C. In mirror, it shows 2C only, na? 2C. So 100% it is obeying the mirror symmetricity rule, correct? So after putting this mirror, so this mirror should be always perpendicular to AB, okay? Always perpendicular to this AB, okay? Na? Now, after keeping the mirror, next point what you have to do is direction of charge. Next, to draw the direction of charge. Most of the student will forget this one. If you forgot this one, you are unable to solve the numerical then. Okay. Now, here the charge Q1 is going in this direction and Q2 is a charge going in this direction. Okay. So in mirror, 100% the charge Q1 should reach here. So if Q2 is going in this direction, the charge Q2 should be reach in this direction. Okay. Am I right? If you observe from a mirror. Is it clear, beta? Is it clear? Chalo. Now, okay. So now see here. So by using this one, you have to solve the numerical. This is a very simple question I have taken here. That's why it is become very easy for you. See here. This is what 2C, 2C. This is 2C, 2C. Correct? Sir, without drawing the mirror also we can solve now. Why you are keeping this mirror and why you are drawing this direction of charges? Sir, it is very confusion, sir. It is not at all confusion. Okay. Based on this rule only, you are able to solve the complex numericals. Without this rule, no teacher can help you. Okay. It goes very complex for you to solve the numericals. Okay. 2C, 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 2C. Without mirror. 2C, 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 2C. Okay. Now see here, beta. So these are same. They are connected in series. What is the formula? C by N if they are same, na? 2C by 2, 2C by 2. Okay. So finally here it is C, here it is C. They two are in parallel. So in parallel, directed addition. Okay. Is it clear? Is it clear? Sure. Next, folding symmetricity. In folding symmetricity, what you have to do is you have to fix this one A and B. You have to fix this one A and B. Okay. Right, beta. So see here, first of all, cross check that does it obeys the mirror rule. So I am keeping a mirror here. Here it is C. In mirror it shows C only, na? But here it is 2C. Mirror is not applicable here then. Okay. Right, beta. So this is what, this is a P, this is what Q, this is a R, this is a S. Okay. Actually this is a capacitor. P by Q equal to R by S. C by 2C equal to C by 2C. It is obeying, sir. Wheatstone bridge is obeyed. Okay, this is removed then. Okay. So finally that circuit diagram how you will get, this is C and this is a 2C. Okay, this is C and this is a 2C. Correct? Correct. This is a final circuit diagram, na? So if you use the mirror also, not at all useful. Correct? Here what you have to do is you have to fold this one. Okay, fix this one A and B. Okay, this is A and this is B. Okay, so how you have to fold is, so from top to bottom you can fold, or else you can fold from bottom to top, beta. Okay, top to bottom or from bottom to top. Top to bottom I am folding. Okay, when these are, when C is coming and falling on C, it becomes in parallel connection. It becomes in parallel. Is it clear? Remember this one. Folding should be up to down or down to up. Okay, gets in parallel connection. Is it clear? So when they get in parallel connection, C plus C, it becomes 2C, na? This becomes 4C. Correct? Am I right? Now, this is A, this is B. So effective. What is the effective you will get? If there are two capacitors which are in series, I said you the trick also to remember. Which formula you have to use? C1 C2 by C1 plus C2. 2C into 4C by 6C. Correct? 2 3s. So final answer what? 4C by 3. Am I right? Correct. So you may get one doubt. Sir, why you are using this folding? Normally we can solve this one, na sir. If you solve normally also we get 4C by 3. I'll show you. See here. In normal method. Okay. These two are in series. If these two are in series, C1 C2 by C1 plus C2. Correct? So what will get, beta? C into 2C by 3C. Correct? So finally what will get? 2C by 3. Correct? Here also 2C by 3. correct? These two are in what? Parallel. In parallel, what you'll do? Both are same, correct? Direct addition, 2 times 2 into 2c by 3. Final answer is what? 4c by 3. In normal method also we got the answer na. Why you are using this folding symmetricity? If you don't know, if you are not familiar about the mirror symmetricity and folding symmetricity, then it means that you have not solved the complex numericals. You have not solved. If you know about this one, then I think you have solved the numericals of this one. Okay, complex numericals. Chalo beta, let's go forward. Effect of dielectric in capacitors. Okay, see here I have taken a dielectric which has a dielectric constant K. The distance separated by these two capacitors is small d. The area of capacitors are A I have taken. Okay, dielectrics are the insulator, non-conducting materials which transmit the electric field without conducting, correct? See here, key point what you have to remember is C is equal to Cm by C naught. Dielectric formula, see here I am writing here. Okay, so in terms of force, what is the formula you got? K in terms of force, ohm. Electric field, ohm. Electric potential, ohm, correct? Potential energy, ohm. Capacitance, it is reverse, more. It is reverse, only one is reverse beta. Okay, remember this one. Is it clear? In metals, K value, it is infinite, remember this one. Okay, Cm becomes 0. So E never enters in a metals. Electric field will be never entering. Okay, Cm formula, K into epsilon naught A by D. C naught equal to epsilon naught A by D. If dielectric has a thickness T, then if this has a thickness T, then you can use this formula beta. Okay, is it clear? This is a very simple only. Okay, based on this one you have some numericals, right? Sir, like this the questions. Okay, here is a K1 they mention. Okay, here is a K2 they mention. Am I right? So you have to calculate the effective of this one. Na? So I'll tell you the tricks. The area of this one is A. Okay, this is a by 2. This is a by 2. This is what? D distance. Na? Like this, such type of questions you have. Na? To calculate this type of questions, use this one. If area is divided, they are connected in parallel. If distance is divided, they are connected in series beta. Okay, remember this one. Without this one, okay, you are unable to solve the numerical. You can solve, it takes a lot of time. But this is the best evergreen trick for you. Is it clear? Right beta. Now, circuit with capacitor and resistance. So I have taken here resistance, I have taken here capacitor. Okay, this is the potential I have applied here. Okay, in the step 1, when I switch on the switch, what happens at time t is equal to 0? Okay, the current flows through the resistance only. Okay, when key is closed, charge becomes what? Here it is 0. Okay, the potential across this one becomes what? 0. Okay, so what is the current across the resistance is what? V by R. Okay, so here it acts as a normal wire beta. Okay, so while solving the numerical, it plays a very important role. Very important role. Okay, please beta, I am covering only the important key points here. Just remember this one. I hope you have solved so many numerical from this chapter, right? So after writing this one, after reading this one, okay, I think you are getting some idea, right? Correct? Sir is taking the imported formulas. If you remember this one, it is sufficient for us. You are getting this confidence or not? Yes? Correct. Chalo beta. See here beta, already you have solved the numericals on this one. Na? You used to do the like this only na beta? Yes? If you till now if you don't solve any single question also, this class goes very tough for you then. Okay, so as it is mentioned in the beginning that this is a summary series beta. In summary we have to cover only the summary itself. Okay, detailedly I can't explain you, but I can explain you these tricks only. Okay, what exactly you have to remember, in which condition you have to use. Okay. Right, brother? So here at time t equal to 0, the circuit look like this. At time t equal to 0, circuit look like this. Okay. Next, you see here, I have drawn here. At time t equal to 0, it looks like this. In step 2, at time t is equal to 0, at some time, after some time, what happens? Slowly the capacitor gets charged, right? Slowly it gets some charged, right? So this is a derivation part you have. It is not required. Okay, not required, not required. Okay, this is a step 3 is important. Step 3, at time t equal to infinite, what happened? This is called as what? Steady state. In steady state, capacitor already gets full charge, right? Capacitor gets full charge. After getting charge, so the circuit diagram becomes like this. Remember, at a time t equal to 0, the circuit becomes like this. Okay, this is a point you have to remember. At a time t equal to 0, circuit becomes like this. You have to remember this one. Okay. Chalo. So if you remember these two, then you will get an idea how to solve the numericals. Right. Note, at time t equal to 0, capacitor acts as a wire. I said you know. Normal wire. At t equal to infinite, it is a short circuit. It means what? Like this. Is it clear? Chalo. Note, as everyone know this one, just now I said to you regarding this one. Okay. Charging the capacitor or growth of charge. Okay. So here I am taking the 3 cases. Just now I said you know, at time t equal to 0, the capacitor. Okay. The circuit look like this. At time t is equal to t. So you have both capacitor as well as resistance. Okay. At time t equal to infinite, steady state, you have a resistance. I said you know, the circuit diagram like this. Okay. Below this one, yaar, super trick beta, very, very, very important. Ekdam jabardast trick beta, this one. Okay. If you observe the graphs, then if you observe the graphs properly, then you are able to solve all the numericals. Okay. Best graph I have drawn this one. See here, initially at time t equal to 0, this is okay, at some time t, at some time infinite. Okay, three cases. Okay, below this one you will be getting. Okay, in order you will get time t equal to 0, time t equal to t. This is at infinite. Okay, charge in capacitor. Initially, is there any charge in capacitor? No. Okay. After some time, there is a charge inside capacitor? Abba, yes sir. Some charge is stored there. What is the charge formula? You go this one. Remember. Khatam. If you remember this one, it is sufficient. All numerical gets solved. All numericals. Capital Q is full charge. Small q is instantaneous charge. Okay, at that instant. Okay. So slowly the charge is increasing inside that one. Okay. At time t equal to infinite, inside the capacitor, charge is full. Okay. At time t equal to, so like this you'll get. Charge is completely full. Is it clear? At time t equal to 0, what is the current across the resistance are very high. Initially at time t equal to 0, current across are very high. After some time, slowly it is decreasing. Why? Capacitor. Okay, the charge is going across the capacitor now. Decreasing. Okay. What is that formula? How it is decreasing? Exponentially it is decreasing. Remember this one. I equal to capital I into E into minus T by RC. Minus T by RC. Remember beta, please remember. At time infinite, is there any current across the resistor? No sir. The completely charge is filled across the capacitor only. Khatam, ring will get drop ho gaya. Is it clear? Chalo. Next. At time t equal to 0, at a time t is equal to t, at a time t is equal to infinite. Is it clear? Now tell me what is the voltage across the resistance? Sorry, it is very high sir, beginning. High. Next. After some time, what is happening, sir? Voltages goes on decreasing. Correct? Where it is increasing? Across the capacitor it is increasing. Decreasing. So exponentially it is decreasing, beta. See here. What is the formula? This one, remember. Best tricks, beta. Best evergreen tricks. Okay, nowhere. No one. So you'll be won't find anywhere this one. Okay. At time t equal to infinite, voltage across the resistance is what? 0. Because total voltage drop across the capacitor na. Correct? Yeah. Okay. Like this will get. Okay. Now across the capacitor. Initially at time t equal to 0, is there any voltage drop across the capacitor? No, sir. Complete voltage drop across the resistance. Na? No voltage. After some time t, what is the voltage? Sir, it is there. Slowly it is increasing. So based on this rate, it is increasing. Like this, okay? At time t equal to infinite, what is happening? What is happening? Voltage goes on increasing there. Am I right? Yes or no? Correct. You got this point now, beta? Okay, because this is a very beautiful trick, very beautiful trick. The thing is, you have to know what exactly RC circuit, how does it works. Okay, so almost you got, I think so. In the beginning, no capacitor, total current goes across the resistance only. Total voltage drop across the resistance only. No? Next, in the middle case, what is happening? The voltage from the resistance. Okay. Initially, voltage is very high. Next, what is happening? Voltage goes on decreasing. This one goes on increasing. Finally, this is full. This is null. Correct hai ki nahi? I hope you got this one. By using this single point, you got this one. No? So based on this one, you have a graphs. Okay. Right, beta. Okay. So finally, it is very full. Na? Correct? So voltage is V. This is VC. Clear? Right, beta. So here, note down e power infinite value minus infinite is 0. E power 0 value is what? 1. Okay. So as everyone know that charge in some time t is this one only, right? So at time t equal to 0, as everyone know that charge is 0 na. So shall I show you the proof? See here. Q equal to, there is no charge in the capacitor in the beginning, right? Q, capital Q, 1 minus e power minus t. T value is what? 0. E power 0. E power 0 is what? 1. What you got? Abba! You got the answer, sir. After some time t, what is the charge? This one. At infinite, at time t equal to infinite, what is the charge? Sir, it is very full, sir. No? It is full. So I'll show you the proof. Capital Q, 1 minus e power, time is what? Infinite by RC. Okay, e power minus infinite. E power minus infinite is what? Something by infinite is what? Infinite only. E power minus infinite is what? 0. This is completely becoming 0. So finally what you got? Q. Khatam. Is it clear, beta? Chal. So you got this one. Okay, at time t is equal to tau. At time t equal to tau. So it is called as what? Time constant. Okay. Charge, we know this one. At this time. Okay. So generally it is getting charging, na? At this time, how much charge will be increased in a capacitor? How much percentage it is increased in a capacitor at time t equal to tau? How much time? So it is 0.63. It nearly about 63% it increases. At this time, what is the charge increases in a capacitor? 63%. At time t equal to tau, charge will be increases by 63%. Okay, of its original charge. Okay, right, beta. So graph between the charge versus time. Charge versus time. See here, at a time t is equal to, at time t equal to tau, 63% it is increasing. Na? So after that one, it becomes infinite only. Correct? These are the formulas you know. Next, similarly, you will get like this. Okay, graph between the current versus time. Current, slowly it is decreasing. So we got this one. Yes. at time t is equal to tau. Okay, see here, at a time t is equal to tau. Tau is nothing but here RC. Okay, in place of RC I am writing the tau. In place of RC I am writing the tau. Okay, time. Is it clear? Slowly it decreases now. How much percentage it decreases? How much percentage? 0.37 times it decreases, beta. Okay. At this time, just remember this one. Increases while increasing, it is 63%. While decreasing, it is 37. I mean, at this time, only at this time it is possible. Okay. Like this you will get. Next, graph between voltage versus time. Voltage across the resistance, decreasing, sir. Again, same graph. Okay. Voltage across the capacitor, capacitors across, voltage across the capacitor, increasing, sir. Increasing graph like this you will get, right? Correct, okay? Am I right? This is what? At time t equal to tau. Again 0.63. Okay. Is it clear, beta? So like this only you will get. Okay, so here are the points I have written. Just note down this one. Okay, so see here, I have drawn that graph here. Is it clear, beta? This is what maximum voltage. Chalo. Next, discharging the capacitor or decay of charge. Okay, now discharging. So just now we have learned about the charging. That is a very beautifully I have given you the all the key points for you, beta, right? So remember that key point, remember the graphs and the formulas, beta. That's it. Okay. Now, in the beginning, at a time t equal to 0, okay, we have a resistance, no? At time t is equal to small t. So both we have. At time t equal to infinite. So the circuit becomes like this, right? In the beginning, during the charging, this is a during charging. Now I'll show you the decay of charge. Okay. Okay. Acha, so I have drawn the graph for this one. Okay. See here. So we have to follow like this now, na? We have to follow like this. Because discharging is nothing but what? The charge is full here. Okay. The next step is this one and the next step is this one. Is it clear? Like this, go in this order. Okay. Main thing is remember the formulas. Okay. And remember the graph. That's it. This is a very beautiful beta. See here. At time t equal to 0, at time t is equal to small t and t is equal to infinite. Okay. Initially, charge in capacitor is very high. Of course, it is starting from here. Slowly, it is decreasing. Okay. With exponentially, it is decreasing, beta. Okay. At time t equal to infinite, of course, completely discharge. Next, current at resistance. Initially, we have to take at high only. Okay. Just remember this one. Okay. Next, slowly it decreases. Okay. Next, completely it decreases. Okay. Next, voltage across the resistance is very high. Okay. Right. Slowly it is decreasing and finally it comes to 0. Okay. Here, voltage across the capacitor. Initially it is very high, na? So slowly it is decreasing. So remember this formula and here remember this formula. So finally it is discharge. Next, discharging the capacitor or decay of charge. See here at time t equal to tau. So here time t equal to tau. Okay. Charge decreases by 37% of initial charge, beta. Okay. See here. Graph. How you will get? Like this you will get. Okay. This initially the charge is very high here. Okay. 0.37%. Okay. At time t equal to tau. This is the time. Okay. Each and every graph you will be getting in discharging like this only you will get, beta. Okay. All are like this only. All are like this only. Just remember the formula. It is sufficient. Okay. See here. Like this only. Okay. Each and every formula, even if you ask the voltage across the capacitor, voltage across the resistance, current across the resistance. Okay. Right. But so in each and every case, you will be getting this one only in this model. Chalo. So next, the current, how it is decreasing, this one only. Okay. So if you draw the graph for this one, you'll definitely get like this only. Is it clear? This is what? Capital I. Okay, this is what? At time t is equal to tau. Okay, this is what? 0.37 I. Is it clear? Okay, chalo. Next, voltage is this one. Voltage across the resistance is this one. Voltage, capacitor. So, okay, voltage across the capacitor is what? This one. Current. Current, what is the current you got? I into e power minus t by RC. So, these three formulas are the imported formulas. Okay, and one more is charge, na? Charge. Small q equal to capital Q e power minus t by RC. That's it. Okay, these are the four formulas. So for four formulas also, you will get the graph like this only. Okay, like this you will get. Okay, so for four graphs, you will be getting like this. At time t is equal to tau, it is 0.37. Okay, whatever the thing you take along this axis, you have to write down there. Next, so here I have written. Next, graph, the same graph. Next, yes, beta. So we have finished the class successfully. So do one thing, note down all the formulas and read all the formulas and practice some numericals from any one of the book. Okay. So thank you so much, beta. So let us continue in the next class. Bye, beta.